I am happy to be here today. I'm going to talk about transporting concrete, but specifically focusing on modeling reactions. I have developed this presentation to research with collaboration with my colleague Jason Weiss. I'm showing you a very long and ugly equation here, and the focus here is not to focus on the equation. That's why I actually blurred out a lot of things. What I want to tell you is that we can model multi-species ionic transport process by solving this long equation. And how you solve this long equation depends on what kind of tools you have. There are very well-established finite element analysis software, commercial or open source, that can actually help you solve this differential equation pretty, I don't want to say easily, but at least, pretty procedurally, it is not that difficult. And, again, I don't want to go into details, but this multi-species ionic transport can involve multiple mechanisms like diffusion, electrical migration, even if you have moisture flow advection. Again, we are not going to go into those today. So the idea is that we know how to solve these concentration of species in a concrete domain, like chloride ion concentration, sodium ion concentration, etc. The trick here is that we know how to solve this equation procedurally, but we need input data. If you have the right input data, solving this equation is actually not that difficult using the right tools. So what are the possible input data? First of all, Keshav in the first presentation talked about formation factor, and he actually showed that formation factor is very related to diffusion coefficients. So if you can look at these diffusion coefficients of each ion, so diffusion coefficient of chloride, diffusion coefficient of sodium, etc., we can actually theoretically calculate those using the formation factor approach. So, you can talk to Keshav more about that, and, we can show you how that's done. We also need porosity. That's the first term that you actually let me use a pen here. That will be much better. Okay, so here, this term here is the porosity term. Keshav didn't show it, but there's a published research on this. You can find it in this reference that he developed a method called modified pore partitioning model that can actually theoretically calculate the porosity of cementitious systems. So from an input point of view, theoretical calculation of some of the input data is definitely possible. But today's presentation about something else. I'm not going to focus on those input data. I'm going to focus on reactions. There's a term in that equation. Again, you don't have to worry about what that term is or how it looks like. That was used to determine the rate of reactions in those in the cementitious system. An example to a reaction could be, for example, when the chlorides are getting into concrete, they may be bound. So chloride binding is a reaction, a chemical reaction. Chlorides can be bound with monosulfates in the cementitious matrix, can be bound with the aluminite and ferrite phases to form Friedel salt, Kuzal salt, things like that. So there are actual chemical reactions that chlorides can have in these systems. And one way of dealing with this, and this is the traditional way of dealing with this, is to use empirical models. So basically, most of you probably are familiar with the concept of chloride binding isotherms. For example, in that example of chloride binding, you actually take your mixture. If you have, for example, if you want to model a concrete, you have to take the Portland cement used in that concrete. You have to take the SCMs used in the concrete. You have to mix them with the right odor to cementitious material ratio. You have to cure them and then expose them to chlorides. And over time, you have to take some chloride testing to see how much of that chloride is bound, and then you actually can draw these binding isotherms, and then you can use those to predict reactions. Now, this is a very time-consuming way of doing it, but the main difficulty is not that this is time-consuming, it's because you have to do this for every single mixture that you want to model. So it is not a generic approach, it is an empirical approach. So there is a disadvantage there. So the question is, can we model these reactions theoretically, as I actually mentioned in the previous slide, as we do for some of the input data? And when I say theoretical, what I mean in this presentation is through thermodynamic modeling. And I'll talk about that quite a little bit more detail later. And that doesn't mean that thermodynamic modeling will not require any input data. Of course, you're going to need input data. So for example, you have to know the chemical composition of the OPC and SCM that you're using. Most of them are available. They come with mill certs. You have to know your water binding ratio. If you know your mixture proportions, you would know this. And you have to know the reactivity of your SCM, which is an important property, but that's also experimentally determinable. So that's something we're going to talk. So when we talk about thermodynamic modeling, this is what I mean. Just briefly, you basically enter the chemical composition of the binder in the system. And if you want to calculate what kind of products that would form when you mix and cure that mixture, that cement material with water at a given time, you can use something called a Pareto and Killoy model to determine how much of these clinker phases would actually react at a given time with water. And then you provide those amounts to the thermodynamic software based on Gibbs-free energy minimization. This is what we are using. There's a modeling package called GEMS that basically minimizes the product, the energy, does an energy minimization to determine what might produce. Again, going into details is not in the scope of this research, but at the end of the day, you can determine how much CSH you form, how much calcium hydroxide you form, other phases. You can determine the pore solution composition, and you can predict things like pH and resistivity. So this is actually a pretty good way of doing it. This is just an example. So you see, you provide the chemical composition of your input. You might have salts in the system as well. And then the temperature, you define your water binding ratio. When you run your thermodynamic simulations, you can actually predict how much of your cement is used over time, these halite, bakelite, aluminate, and ferrite phases, and how much products you form, Portland, CSH, ettringite, etc. So it's a very powerful tool, and this is not something we discovered. Obviously, a lot of people work on these kinds of works. So there are a lot of people who need to take credit in developing these tools. The way we use it, though, we actually use these in a reactive transport approach. As I said, that long and ugly equation, it needs the reaction component. So while we are solving the reactions, transport problem using the finite element approach, in a time marching algorithm, for example, when you're running these simulations at let's say 10 seconds, every 20 seconds, in each time march, you also call the thermodynamic calculations as well. So you actually calculate the state of the chemistry in your system. So that is the idea how we use the coupled approach. And we developed different versions of this a number of years ago. It's been almost now 10 years now. We actually coupled a commercial finite element package called COMSOL with open source thermodynamic modeling code called GEMS. We use this. This is published already. You can find some literature on this. We used this for a while, but this became pretty complicated because commercial softwares are updated and the versions become obsolete, etc. So keeping this interface maintained was very difficult. So we went to a different path. We are now using a completely open source finite element package developed by US government, and also still coupling it with a thermodynamic code. So going back to that equation, that ugly equation, now I probably understand what I mean by thermodynamic modeling. And when I say thermodynamic modeling, as I said, it's not going to work for everything because some reactions will require some kinetic input as well. Thermodynamic models can predict things at infinite time, at equilibrium. So for the reactions that require kinetics, we'll have to do something else. So that is something that I will talk about briefly. But before that, I want to show that we have done extensive benchmarking of this approach, benchmarking with different types of reactive transport codes. And we have seen that we actually can benchmark pretty well. Now, examples. When I say how we model reactions, one example I gave was chloride binding. Now, these are results of such an approach. The plots basically look, complex. I'm not going to spend time, deciphering everything here. But the message here is that whether you're modeling an OPC system or OPC or plus slag system or OPC plus fly ash system, we can actually predict chloride binding isotherms. These are chloride binding isotherms. Vertical axis is the bound chlorides, horizontal axis is the free chlorides. We can predict chloride binding isotherms very accurately using thermodynamic modeling. The message from here is that you don't run experiments to get these algorithms, you theoretically determine them. And you can use them in that reactive transport algorithm, solve those equations coupled with the thermodynamic modeling. So you can actually predict chloride profiles. These are free chloride versus the distance this is, I believe, an OPC system, and it's an OPC plus fly ash system. We can see that we can get pretty close match to traditional approach that uses experimentally determined chloride binding isotherms. So that's one example. Another example is to actually model with SCMs. This is something that we pay a lot of attention to. When you have SCMs in the system, the reactions become more complicated to model. You actually, for example, fly ash will have these compositions that you have to deal with, but also fly ash does not react completely. So you have to modify the kinetic models like Pareto and Killoy model to calculate how much of the fly ash is reactive. Then you can use GEMS properly. So there's a kinetic side of things. You can fool or you can deceive, in a way, the thermodynamic modeling software to do some kinetic calculations for you. And there's a paper here. There are two papers here you can actually see. And I will show you that if you do that, if you don't do that, let's do it this way, if you don't do the kinetic approach, if you try to model things using the bulk chemistry of the SCM without even thinking about how much of it is reactive, you can see that you cannot predict things well. This is actually, vertical axis is the calcium hydroxide amounts that are modeled, and the horizontal axis, the calcium hydroxide amounts that are measured. Calcium hydroxide amounts are indication of the pozzolanic reaction. Pozzolanic reactions consume calcium hydroxide. That's why we are interested in that. So if you don't use that kinetic approach, you can see that you cannot predict things very well. But if you use the kinetic model, you use the thermodynamic / kinetic approaches, you actually can predict things pretty nicely. So you can say that actually, even the problem has some kinetic component in it, you can find ways to do this. And this is an example, or maybe an illustration of why this is important. So if you actually did not use that kinetic, we assume that 100% of an SCM is reactive, that means that it is going to be available for reaction from the beginning. So time-dependent properties of that reaction is not going to be accounted. But if you also consider the SCM to be time-dependent in terms of its reactions, you can take care of the time-dependent properties of the reaction. So that's why kinetics is important. And you can see that when we use this modified Pareto and Killoy model that was developed by our PhD student, Deb Glosser, who is an assistant professor right now at an institution in Washington, you can see that for different phases of LCMs, we can actually predict how much is going to react pretty nicely. And when you use those things, you can actually predict things very well using that thermodynamic approach. You see, these are the calcium hydroxide amounts, and these are the pH values that we predict. If you don't use them, you can see that without using that kinetic approach, you're going to get into problem. You don't actually get any meaningful results. So where we're going with this, I think Keshav mentioned this a little bit in the first way. We want to get the raw materials, compositions, reactivities, do some preliminary testing and use these modeling approaches to find the properties of the paste, upscale them to concrete, obtain things like formation factor, diffusion coefficients, etc., and do reactive transport modeling to actually do what we call a self-sufficient modeling. So what our ultimate goal, and we are actually very close to this goal, is that we want to solve this ugly long equation without the need of doing any experiments. We want to calculate all the input parameters like porosity or diffusion coefficients and activities using theoretical approaches. And we also want to make sure that we can model reactions theoretically. So that was my presentation. I will be more than happy to answer any questions now, or we can also discuss things after the session. Thank you so much.